Drop a needle on lined paper at random. The average number of crossings involves pi, and we're going to see why without ever computing an integral. Picture parallel lines on a page, evenly spaced a distance d apart. Take a needle, no longer than that spacing, and let it fall at random. Once it lands, we count how many lines it crosses, and we call that count n. For a short needle like ours, n is either 0 or 1, since the needle isn't long enough to reach two adjacent lines. The question is, across many random drops, what's the average value of n? Here's the key observation. If you doubled the needle's length, you double the average number of crossings. So that average is simply proportional to the length. We can write it as some constant c times L, and the whole problem reduces to finding what c is. Now suppose, instead of a needle, we drop a curve, any shape at all. Slice it into many tiny segments, each one essentially a miniature needle. By the same proportionality argument, each segment contributes c times its own length on average. Linearity of expectation lets us add them up. The total expected number of crossings for a curve of length L is just c times L, the same constant, regardless of shape. Since the answer doesn't depend on shape, we get to pick a convenient one. The clever choice is a circle whose diameter is exactly d, the line spacing. Drop this circle anywhere on the page. It crosses exactly two lines, always. Its length is pi times d, and its expected count is 2. Plugging into our formula gives a single equation, and that equation pins down c. It must be 2 over pi d. Returning to the needle, the average number of crossings is just c times L, which gives 2L over pi d. Here's a practical bonus. The formula can be rearranged to estimate pi from samples. Just multiply twice the needle length by the number of drops, and divide by the line spacing times the number of crossings. With about 2,000 drops, the approximation is already accurate to 2 decimal places. For a short needle that crosses at most one line, this expected count is also the probability of a crossing. The whole result, pinned down not by an integral, but by a single circle dropped on the page.